Hello again. You know, it amazes me how computers actually function. Just geniuses that enabled us to have this technology. We're going to take a look at, well, what Test Out wants us to look at so that we can get this certification. So you see here on the screen, we are looking at information technology basics, and we're taking a look at the digital data portion of this, talking about numbering systems and talking about data representation. And so to truly understand, build this information into our heads, we need to take a look at what's happening inside a computer. Now, the instruction set is something that I talk about often in different classes. There's usually not a definite test over this information, but I find it fundamental to be able to put it in your head so that you can build this information on top of that. One of the largest complaints that I get from students is that there's so much information as we get moving forward in technology. And really why that's a complaint is because your brain has to be able to link things together. And if it has some way to link it, it makes it easier. And that's the purpose here today, is to kind of show you, hey, we're dealing with some levels of programming, levels of interpretation, you might say, so that a computer can actually do what it needs to do. So we can make it do what we need it to do. So let's take a look. There's levels of programming here. So there's the very top of it, very visual languages. That's what we're getting to. They're trying to make it easy enough that almost a normal person could build a simple program. Then we deal with Fortran, C, Pascal. So if you're dealing with Visual Basic, Visual Studios, right? That's up here. And then the Fortran, C, and Pascal, right? 60s languages up through the 80s. And these are all high-level languages. So that's all grouped together. That's why they've got this kind of built in here together. High-level languages. The reason they call them high-level languages is because there's things below them. This is where we sit. In other words, this is where we program, we make things happen here. But the computer way down here needs it to be different, right? It needs it to be binary. So let's look up a text binary converter. You may not have known those exist, but they do. So let's just do a unit conversion here, and let's input some text to binary. See, so this converter says text to binary, to bin numbers. So I would like to learn how to program binary. And as I've typed here, you can see what the binary value is. Now, can you imagine actually having to learn what each of these sets means? It's also a lot longer, right? In order to actually present one of these letters in these spaces, I've got a binary value for each one of them. Back up. I. Space I. Notice how that's different. Lowercase and upper, right? It has to have a way to do that. O, U, 75. Money sign. So very short text. We can clearly, I owe you $75. That's what that means to us. Our brains can interpret that. The computer cannot. We have to provide the interpretation for the computer. We have to tell it what all this means and how to convert that all the way down to binary. So as discussed in this unit, binary really can be set up with any single two states, right? So we have to have a 0 or a 1, 0 or a 1, 0 or a 1. Now you're like, why does he keep repeating that? Because for each of these that you see, this could be a 0 or a 1, and this could be a 0 or a 1, each of those spaces. So it's base 2, right? Two different spaces, two different values for a space, sorry. Right, so that's binary. That's how the computer talks. We could use wireless signal, no wireless signal, electrons, no electrons, electricity, no electricity. That's what that means. Light, no light. Or we could say light, different light. We could say one voltage, a different voltage. So as long as you can have two values, then you can have binary. And that is how the computer is functioning. Way down here, this machine language is binary. That's what it is. In other words, the native tongue of the computer. Right? This is the ones and zeros. Then we take it up a step from that. So when you get to this portion in the 100 or 170 class, it starts talking about assembler. And that specific code that's been put in there so that the computer can have different instructions, right? Once we get to the point where computers are doing the same things that we want them to do over and over again, we can codify a process. We can make ones and zeros represent a certain thing, like take this result the CPU just created and store it over here in this temporary cache. And so we can actually create codes that would mean that. Now you will look at this and go, wow, that's still just so much. How would anybody figure this out? But the truth is that's what it has to be. We have to have a set of instructions that the CPU can actually use. Now I've actually, I don't want that. There's ENIAC. That's not what I want. Oh, let me just pull it up. So an instruction set is something that the CPU will have in it. In other words, a set of instructions that the CPU knows how to deal with. And here's some examples that have been added in. For instance, AMD became big in gaming, or bigger in gaming, as a gaming CPU, because they said, you know what, in order for programmers to make this visual thing happen on the screen, they have to go through these different instructions to make that happen. So why don't we include a special set of instructions that will reduce what they're doing here? We'll just put that in here, and they can call that and say, I need you to do this, and that instruction will do what it needs to do. That makes it easier for programmers, right? When you look at the levels of programming, they're programming up here. That's where they're programming. So to be able to call an instruction down here in the assembly language, that's awesome for them. That's going to make it easier. So we talk about these layers in computing quite often. We use these layers. And the reason why we use these layers is because inevitably you're coming down to ones and zeros, and none of us want to deal with having to have ones and zeros. So there's going to be a set of programmers out there that are saying this set of code, which is very cryptic, is going to mean this in binary. So then that way, these higher level languages can say, okay, I can go ahead and deal with that code instead of having to deal with the binary. That's what this comes down to, data representation. How is data represented, and how is that converted through the system? So let's take a look at some data representation facts. Well, let me just show you the numbering facts here. Just it's kind of showing you, hey, we use the decimal system. Computers use the binary system, and hexadecimal systems are something that's in between that. So this is a numbering system that is used to help in programming. And that numbering system, hexadecimal, goes quite a ways back. But it's basically a way to say, I'm going to have different values. Notice that this number here starts with 57, 69, and then it's got a 6B. What's a 6B? What's a B doing in the numbering system? Well, hexadecimal uses letters A through F, and it doesn't matter if it's capped or not. That's what they're trying to tell you. And those values are going to equal 10 through 15. Now you realize, right, 10 through 15, that's only 15 digits. Well, not really, because we also have 0. We count that as a digit as well. And so that's 16. So we can represent things of 16 within this. And doing so, oh, that's memory address space is usually represented in hex. We use, whoops, it went a little too far there. The Unicode standard, it uses hex. So you'll see that 20 AC. The reason I focus on hex, what hex means, you can see that it's used all over the place. It's used all over. It's used in programming, and it's often things that you're looking at when you're dealing with hacking, because when you look at a memory address, it's being stored in hex. And then knowing, oh, that's Unicode that's storing it in, you can convert that over to what it means. PostScript uses hex, basic, quick basic, free basic. There's just tons. You can take a look here. And IP version 6 uses hex in its addressing schemes so that there's more addresses available in a smaller space. So hex is used quite a bit. Jumping back over to test out here. And it gives you basics of how each of these works. Usually when you start seeing math stuff, you're like, this is really gonna cause me an issue. And the honest truth is this is something to know. Right? This is something to have in your head. Like, I realize that data representation is happening because I need to get down to these ones and zeros. They're actually showing you how that happens. If it's a 1 here, what does that mean? If it's a 1 here, what does that mean? Which is nice, but unless you're trying to impress somebody at a party, yeah, that's not going to happen with this, right? Then really you're not doing this, but maybe if it fascinates you, you'll be one of those people that'll do the translation between binary and machine language, assembler. So here's our hex system that really explains, and I would spend a little more time focusing on this portion so that you understand how hex is functioning, because again, it is used in network addressing. It's used in Unicode and ASCII and all those things of basically saying, oh, and colors. So this page here where we get this background color and this background color on the page, that's being defined in hex someplace. And security-wise, hex is used there as well. All right, I'm gonna stop this video and we will continue on this little journey. Just a second.